Hello, in this video we're going to be using the Crank-Nicolson method or the implicit differencing to write a code for the thermal profile of a bar. So this is similar to a problem that we did in a previous video, except in that video we used explicit differencing. And the reason we're changing the method is because with explicit differencing there is an upper bound to what the constant or the variable we named as r is, and so r is defined as the thermal diffusivity times the time increment divided by the space increment squared. And so there was an upper bound because once you reach that upper bound, what would happen is there would be instability, and so that's why we were given that the max time step was 0.5 seconds, because the thermal diffusivity and the space increment were both 1, and so once it reached past 0.5, instability would occur, and we did a von Neumann stability analysis on this to show why that was the case. And so in this video we're going to be using Crank-Nicolson method, which the difference is instead of just using the temperatures at the next time step, we'll be using the average of the temperatures at the previous time step and the next time step, and this will get rid of the instability. And so that occurs when we look at the approximation. So the approximation of the derivative of temperature with respect to time remains the same. And so before we begin, in the previous video we discretized the space increments and the time increments, and so the position x is the counter j times the change in the position or the space increment, and then the time is the counter n times the time increment. And so we'll be using the same counters just to keep it consistent between videos. And so the approximation for the derivative of temperature with respect to time is the same as it is for explicit differencing, and so that's going to be the temperature at the same positions at different times. So we'll do the time n plus 1 and the time n both at position j. And so it will be the sum of these two over the change in time. The biggest difference is going to be the approximation of the second derivative of temperature with respect to position. And so the alpha remains the same, but what happens is in the previous video we had the temperatures at 3 different positions, 3 different space increments, divided by the change in the space increment squared. And so we had it at t, the temperature at the next position, temperature at the current position, and the temperature at the previous position, and they were all at the time n. And then we had 2 of the current positions based on the approximation, and so it would be tj plus 1 at n minus 2tj at n plus 2tj minus 1 at n divided by the change in x squared. And so the only difference is now we're going to do it at the next time step. So we'll add it. So we'll do the same positions. So tj plus 1, tj, and then tj minus 1, except now we'll be doing it at the next time increment, so n plus 1. And then it's the same thing, it'll be divided by the change in position squared. And since we'll be taking the average of these two values, we'll be dividing by 2 because there's 2 values, so when you average you sum and then you divide by the number of values. So we'll just move the 2 out here just to keep it a little clean. And so now what we're going to do is we're going to distribute out the delta x squared and move the delta t to the other side and just clean it up a little bit. So we'll have tj at time n plus 1 plus tj at n is equal to alpha times the time increment divided by 2 times the space increment squared times, so we have t temperature at position j plus 1 at time n minus 2 times the temperature at position j at time n plus t times temperature at position j minus 1 at the time interval n plus 2 at position j plus 1 at the time n plus 1 minus 2 times the temperature at position j at the time n plus 1 plus the temperature times at position j minus 1 at the temperature n plus 1. Whew, what a mouthful. Okay. And so in the previous video, this is where we had the constant r, and that's what had the upper bound. Just to avoid confusion, we're going to change the variable name to u, just so that when we go into the code and are comparing and looking at the two different types of methods, there is no confusion. And so the u will be distributed to all of these values, and then we're going to move all of the times from n plus 1 to the left side and all of the times at n to the right side. And so we'll have negative u, which is this interval, at times the temperature at j plus 1 at the time n plus 1, temperature at position j plus 1 at the time n plus 1, plus 1 plus 2 u that's times the temperature at j at time n plus 1 minus u the temperature j at position j minus 1 the time n plus 1 is equal to u times the temperature at position j plus 1 at time n minus or plus 1 minus 2u times the temperature at position j at time n plus u times the temperature at position j minus 1 at time n. And so now we have all the like terms on the same side. What we can actually do is create a matrix, and this is what the matrix is what we'll be using in our code. And so we'll start with the left side here. So we'll have the temperatures. So in the bar, we are given basically in the problem statement a bar with known values on either side, and then the increments of the in between. These temperatures are what we are solving for. And so we start at the first temperature, and then we'll be going down. So the temperature a little bigger, position 1, 2, 3, all the way down to how many ever increments there are. We'll do one more actually. So temperature at 4, so we have the room for it, and then down to n. And so what we have over here is it will be the values. And so position 2 at 1, we'll start with the second one, and we'll come back to this first one. We'll have the negative u, because at position 2, j plus 1 be the previous, and then we would have 1 plus 2u, and then we would have negative u again, and then we would have, and then for the third temperature, we would have a 0 here, and then we would have negative u, 1 plus 2u, negative u. These would just be zeros. And then for the fourth one, we would have 2 zeros, negative u, 1 plus 2u, and then negative u. And then for all the times, or all the temperatures in between. And then finally, for the last one, we'll have negative u, and then 1 plus 2u. And so that's the left-hand side of the equation, the matrix, excluding the first one. And so the reason for this is because the temperature at 2, so J is equal to 2, at J, or at the third temperature, we would have a negative U, and then J at 2, we would have 1 plus 2U, and then at J minus 1, so at the first temperature, we would have a negative U. Same for the third one, so 3 plus 1 is at the fourth position, so 1, 2, 3, 4, we have negative U, and then at J, 1, 2, 3, we have 1 plus 2U, and then at J minus 1, so 3 minus 1 is 2, 1, 2, we have negative U, and there is nothing, there's no 1 value, and so that's why I have a 0 here, and it goes all the way down. And so finally at T plus N, we don't have a value because there's no further temperature, so there's no negative U. At Tn, we have 1 plus 2U, and then at the previous value, we have negative U. And so that's the left hand, excluding this first row. We'll come back to that. So on the right side, so basically this left side is T equals N plus 1 times the time increment. And so over here we have the time is N times the time increment. And so we'll start again with the 2, or the temperature at position 2. So at J plus 1, so at 3, we have U. And then at 2, we have 1 minus 2U. And then we have U. And then so we have J minus 1, that would be T1. And then we have J, so just T2. And then we have T3. And then so following that same pattern, we'll have the U's constant and the 1 minus 2U. So 3 plus 1 is T4. 3 is J, so it just remains temperature at 3. And then 3 minus 1 is 2. Similarly, 4 plus 1 is 5. 4 is the same, so T4. And then 4 minus 1 is T3. And so when we're looking at this, for the first value, we have plus 1, so U, T2. And then we have just at the J, so T1. And then for this one, we have the T naught, or the initial T. So again, when we talked about that bar, we have the known value at the beginning and the known value at the end. And so the known value is the same no matter what. And so that one doesn't change. But over here, we also have that same thing because this T1 minus 1 is going to be the T0, and because it's constant, it's going to be the same here and here. And so what we can actually do is move this over to the other side. So we'll have 2, because negative, so plus T2U T naught, so it remains the same. And then down here, it will be the same because it'll be the last value. And so we'll have TTU Tn, and then 1 minus Tu U Tn minus 1. And so this is the final value, and same thing, it's constant, so we can move it to the other side, and we'll have 2 of it. And then lastly for this, T minus 1, again, we move it to the other side, so there is no value here, or excuse me, there is no value here. And then at the third position, and then here we have just the 1 at the, we have the negative U, and then we have the 1 plus to U. So these are zeros. And so that is our matrix completely filled out. And if you look, you can see that there are these kind of diagonal bands within the code here. So we have three kind of diagonal bands here. We have this one that goes fully from the top left to the bottom right. So that's our main band because it's through all of it. And then we have the upper band, which doesn't have a value up here, and so it starts kind of shifted to the right. And then we have the lower band, which doesn't have the value in the bottom right, which is kind of shifted left. So we have three bands, and that will become important because in our code, that's what we'll be using to solve for the temperatures. Okay, so before we jump straight into the code, I made one mistake with the matrix here. The n, there obviously these two are contradicting because they're both the temperature at n, and so what we'll have to do is this middle one is actually n minus 1, and then this last one is n minus 2. And so the reason for this is because this is the known final temperature, and so this is the previous one, and then it's actually the one before that, and so that will become important when we put it into our code. So now we can begin coding, but let's look at the previous code we wrote really quick. And so this is the code that we wrote for the explicit differencing. This is the graph that we got. So to show if we were to change the time increment past the upper bound just by 0.01, it creates this instability. And so that's why we're doing the Crank-Nicolson method. And so we're going to hope to avoid that in our final code. And so we'll be using this little prefix, the scipy lin_ouch.solve_banded. This allows us to solve banded matrices, and so we'll need to create our bands, and then these are the parameters that we'll be using once we actually solve the matrices. And so to begin, what we need to do is input our inputs, and so they're actually very similar to the explicit differencing. It's the same problem, we'll just be changing a few things. And so the first thing we'll be changing is that there's no R anymore. It's now, we renamed it U, and we are taking the average, and so we have that 2 in the denominator. So it is the thermal diffusivity times the time increment divided by the space increment squared times 2. And then we're going to be also changing the initial values of the temperature, and we're going to rename it TI just because it's not, the T0 makes it seem like it's the first index of the temperature. It's not, it's just the initial values that will be going in our array. And so everything else is going to stay the same, space increment's the same. For now, the time increment's the same. We'll be changing it around to test the stability. Thermal diffusivity is the same. The constant temperatures on the left and right side of the bar are the same, and the the number of steps are the same. And so we'll shift enter. So now what we need to do is we need to create our bands. And so we'll just call it bands, and we'll create just zeros to start, just to fill it up. And so there's going to be 3 bands, so there's going to be 3 rows, and then for columns we'll have the number of steps, but because the first value is constant, on the left, and the last value is constant, we'll have 2 less than the actual number of steps, so we'll subtract 2. So if we look at our bands, that's what it's currently looking like. And then we need to create our first band. So our upper band is just negative U, that's the value of it. And so it's going to be the first row, and then for all of the columns after the first one. And so as you can see, this first one remains 0, which is how it is in our matrix that we wrote on the board. And then the next one is our main band, so that is 1 plus 2 times U. And so that's going to be our second row for all of the columns. So now we have, Python indexing starts at 0, so our second row is actually going to be 1. So it fills up this row here. And then lastly, our lower band is also just negative u, and that's going to be our third row, so 2, and then it's going to exclude the last value. And so as you can see here, this last value is 0. So those are our bands. So now what we need to do is create our kind of initial array for the temperatures. And so we did this for explicit differencing. So we're just going to copy and paste to make it easy. And then we'll do a little bit of renaming to keep things clear. So this is for implicit differencing, and we changed all of our values to the initial value TI of 25. This is to define the first value, which is known, and it's constant. That's 50, so that's on the left. And again, the next thing starts at 0. And then our last value all the way on the right is 80, and so we have that defined up here, and we put it in here. So if we shift enter, we can look at that array now. Oh, we have to change all of the values, or all the names. So now we have our initialized temperature. So now what we have to do is we have to create our right side matrix, and so that is what stays the same is the U, so it's U times the temperature array, and then we'll input that in just a minute, and then we have plus 1 minus 2 times U times the temperature array, and then we have plus U times the temperature array. And so what values are within the array? Well, the first one is going to be 2 because it's the second. We'll be using this second, so the third value in the array, but it's the second of the, so if we were to just grab the main values here, or the values that don't remain constant, so we'll do 1 to -1. These are the initialized values excluding the constants, and so we're trying to grab this value here, which is T2, and so that's why it's the second value of this slice of the array. It's the third value of the actual array, which is the index 2, and that's going to be for all of the columns. And then this one is just the current value, so that's just going to be this here. So 1, -1, and then for the last one, it's the very last value, and so we'll do -2. And so that's that. And then if we look at our matrix, the first value of it is that first value plus, and then we have the value of the previous. So when we did the matrix in the first row and in the last row, we had that tricky little, we moved it from the left side to the right side of the equation, then we had 2 times U times Tn or T0, and so those values stay the same because they're constant, and so that's why we have to initialize them, and so it's just U times, and then the value would be, for the first one, it would be T0, so we would do, and then for the last one is similar, just -1 instead of 0. So we have that now. So if we were to look at RSM, this is our kind of values from the right side of the matrix, or the right side of the equation, the matrix. And so now what we need to do is we actually need to solve the matrices. So that's what we'll use the from scipy dot lin alg. We'll import solve underscore banded. So we'll shift enter all the way through so that we're able to use it. And so for solve banded, the parameters are the number of non-zero lower and upper diagonals, so the upper and lower bands. So we have one upper and one lower, and then we have the actual banded matrix, and then we have the right-hand side. And so we're going to put that straight in. So we have one upper, one lower, and then our bands, and then we have the right-hand side of the matrix. And so now it's solved. And so now what we need to do is we need to put it into a loop so it continuously solves it and then can graph it. And so we'll use the same loop that we used up here. And we'll need to put this within the loop. So put loop, so it will loop through, and we'll want to graph it, so we have to actually initialize the graph as well. And we'll call it fig2 just to avoid confusion. So if we shift enter, what did I do wrong? Oh, we need the x. So the x values. Maybe. So realizing my mistake, this is why copy and paste can be very helpful but very detrimental, is I renamed my temperature array and did not change it within the graph for the y. And then also I did solve banded, but I didn't tell it where the solve banded values were supposed to go, and they're supposed to go in the temperature array. And so it's going to go for the values, not the constant value. So starting at the first non-constant value, which would be the second value in the array, which is indexed with 1, and then going all the way up until the last value. That's where the solve banded goes. And then if we shift enter, now we have a graph that shows the thermal profile of the bar. And so just a few things. First thing we're going to do is just to change it so it's labeled with the actual time and not the number of iterations. We can do times dt. And so now that's the time that it's taking. And let's just show that there is no instability. So earlier we had instability when we would go to 0.51. So just to show that again. And here we can do the same thing. We'll do that. So with the different times there was instability. Now if we were to go down here and go 0.51, there is no instability. So that's the differences between these two methods and these two graphs. But 0.01 isn't much more than the upper bound. So if we were to go to, let's say, 0.8, there is still no instability and it still reaches steady state. The only thing about it is it may not be extremely accurate the higher the value we get. So if we were to just look at this value here at 10. It's at 48.7, we'll say 48.7. So if we were to go to maybe 0.2, at 10 it's, or at, let's say the 40, we'll redo this. So 48.7, if we go to 0.8 again, oops, not sure what I did there. And we look at the 40, it's also about 48.7, so it is accurate here, but sometimes the higher you get, it can get more inaccurate, especially when we start having larger numbers and larger data sets. But that is the code for the thermal profile using banded matrices, and so this is what it looks like.